Hello there. My name is Isaiah Poor, and today I'll be talking to you all about surface integrity and surface finishing. First, I'll go over a few simple terms, and then I'll talk about two research projects that I found intriguing. So, without further ado, let's jump right in. What is surface integrity? Surface integrity is the nature of the surface condition that is produced by the manufacturing process. This process could be workpiece, tool, machine tool, environment, and process variables. What is surface finish? Simply put, surface finish is a wide variety of surface textures generated by the material removal process. And if you look at this figure on the left, you're able to see three different material removal processes: horizontal milling, vertical milling, and turning. And if you look down here, you're able to see that as the average surface roughness decreases, the smoothness of each surface increases. The first research project I'd like to talk about is surface integrity of GH4169 affected by cantilever finishing, grinding, and the application in aero engine blades. This project was conducted by Xung Li, Shuang Mao, and Fanjung Meng of the School of Mechanical Engineering and Automation from Beihang University in Beijing, China. Excuse me for my pronunciation. So some background for their project. Poor milling performance would affect the surface integrity of the blades. This was important because it directly influenced global performance and reliability of aero engines. Fatigue failures of rotor blades accounted for more than 50% of major aircraft engine failures. Finished surface integrity, especially surface roughness and residual stress, has significant effect on the fatigue life of an individual blade, and then on the global reliability of an aero engine. GH4169 is the main material for aero engine blades and integrated blisks. And for those of you who don't know, blisks are essentially the front view of turbines, basically when all the blades come together into their circular formation. So what method were they using to make the blades before? GH4169 blades were machined mainly by numerical control milling process. This process limited further improvement on machining precision and surface integrity because of fast tool wear, cutting chatter, and cutting forces. So what did they do during their experiment? Through grinding experiments on parameters and surface integrity optimization, the helical cantilever grinding process, utilizing a 300 CBN RB wheel, was presented and applied and finished machining of the GH4169 blades. This slide here paints a good picture of what cantilever grinding looks like for y'all. In this figure on the left, you have the fixture here and the workpiece, which is the blade. Then you have the wheel, and the wheel will follow the arrows as its path. And this figure on the right is the same thing, just from a different perspective. You got your workpiece and the wheel path, and it's just working its way down or up. So what happened during their project? The profile errors of the blade surface were within 0.01 millimeters. The roughness was less than 0.4 micrometers. The residual compressive stress and the hardening rate were deemed appropriate. There were no phenomena of burr and smearing with the grinding chips. So how did their project finish out? The surface residual stresses were measured in the middle of the suction/pressure surface. The average values were about 700 megapascals and 540 megapascals in two directions respectively. The surface quality of blade surface was stable and no defect phenomenon happened on the finished surface. Conclusion continued. The leading/trailing edge can be smoothly connected with the suction/pressure surface and has a high profile precision, which shows clearly that the helical cantilever grinding process, utilizing the 300 CBN RB wheel, is very suitable for the profile finish machining of GH4169 blades, and moderate surface integrity can also be achieved. The second research project that I found intriguing was the experimental study of surface finish during electrode discharge machining of stainless steels. This experiment was conducted by Carlos Mascarque Ramirez and Patricio Franco. Once again, forgive me for my pronunciation. Some background on their project. A series of experimental tests about electrode discharge machining of AI-SI 316 stainless steel using copper electrodes were carried out. The surface roughness parameters were registered and scanning electron microscopy (SEM) was applied to analyze the surface integrity. The workpiece that was used was 40 by 40 by 10 millimeter plates of AI-SI 316 stainless steel. The project was carried out from 6 to 14 amps. So what is EDM? EDM is a process which removes metal by discharging electric current from a pulsating DC power supply across a thin inter-electrode gap between the tool and the workpiece. And this figure on the right paints a pretty good picture of that. Here you've got the DC pulse generator. Here you've got the tool, which is the negative portion of the circuit. Right here you have your workpiece, which is the positive end of the circuit. And right here, in an auxiliary view, you can see the dielectric gap. Now a brief video on EDM. Excuse me. So what is SEM? What is SEM? SEM uses a focused beam of high-energy electrons to generate a variety of signals at the surface of solid specimens. Signals that derive from the electron sample interactions reveal information about the sample, including external morphology, chemical composition, and crystalline structure, and orientation of materials making up the sample. This GIF here paints a better picture of how SEM works. Here you have the high energy beam of electrons being shot at the specimen. It is then being picked up and read by the SE detector, which then goes to the computer, and then the worker is able to read the data off of the monitor. Here are some results from their project. On these two figures on the left, you're able to see that current intensity and surface roughness are directly proportional. And the RT here is for max profile height. The two figures on the right, you're able to see that current intensity and surface roughness is also proportional. RA in blue is the average surface roughness, while the RQ in green is the root mean squared roughness. Some more results from their experiment. These are SEM images of machine surface for current intensity of 6 and 12 amps for EDM test with a penetration depth of 5 millimeters. For the figure on the left, you're able to see that the crater diameter is much smaller than the craters on the right. So in conclusion, for their experiment, they noticed a linear increase in both the surface roughness and crater diameter as a function of current intensity. They also noticed that current intensity wears great effects on surface integrity. And this figure here shows crater size as a function of current intensity. And you're able to see that current intensity and crater diameter are directly proportional and hold a linear relationship. These are my resources that I used for my presentation. Thank you all for your time. I hope you'll have a good day and a good end of the year. Thank you.